Hi, my name is Moshe Sipper, and I'm going to present our work on coevolving artistic images using OMNIREP. This is work done by Herein, Urbanowicz, Jason Moore, and myself, and we're from the Institute for Biomedical Informatics at the University of Pennsylvania. Before I begin, I wanted to present a few other things that we've been doing, and I want to mention that everything I'm going to talk about is on my website. It's actually on my homepage, so you don't even need to dig in. You'll find all the links on the homepage. So if you're interested in genetic programming, I think this paper, you might find it interesting. We looked at the GP-TP workshop, which focuses on GP, and we kind of examined it through 15 years. So it kind of gives a nice perspective of GP, and that paper is out, and like I said, you can get it through my website. There's a tiny GP in Python that I wrote. There's two versions. One is a bit smaller, less fancy graphics, but they're both small, and it's kind of nice if you're getting into GP or if you teach GP. Has all kinds of uses. We have this interesting little piece on AI in Newsweek, kind of a sobering outlook with all the hype. So that's out there too. And I want to mention our Pen AI project, which kind of aims to bring AI and ML, machine learning, to the non-expert. So let's get to business. We have been looking into evolutionary computation in general over the past 2-3 years, and we've been sort of examining some basic issues. So we examined the issue of parameters, we examined the issue of representations, which is actually the focus of this talk, and we examined the issue of fitness, and all of these eventually ended up as papers that are out there for anybody who's interested. We performed some extensive experimentation regarding parameters in evolutionary computation, and we came to some interesting conclusions. I'm not going to say any more about that. This is kind of just a soundbite. We did a lot of things with coevolution, and that's actually going to be the focus of what I'm going to talk about in a couple of minutes. So coevolution, there are basically three kinds. There is cooperative coevolution, where you have a number of species that cooperate to attain better fitness. There is competitive coevolution, where you have species in competition with each other, predator-prey, for example. And there's something called commensalistic coevolution, where you have, say, two species. One species gains benefits, the other isn't harmed, nor does it gain benefits. We're going to focus on coevolutionary computation, where you have multiple species with a couple of fitness. Specifically, we're going to be focusing on two populations. And the issue that we are interested in is the issue of representations in evolutionary algorithms. So, as we all know, a given representation might be preferable over others. Okay, that's actually one of the most important decisions you have to make as a practitioner of evolutionary algorithms, is what is your representation. But if you think about it, what we often do is kind of conflate representations and encoding. So we might say something like, oh, I'm using this 100-bit bit string, and it represents 4 numerical values, and each one is encoded by so many bits. But actually what we're saying is we've got a representation of that's a bit string, and we've got an encoding that kind of decodes how to read these bits. That's actually two things. And the basic idea in OMNIREP is, okay, let's take these two things and separate them into two populations. So now what we have is we have a population of encodings and a population of representations, and they evolved separately as single population evolutionary algorithms. So crossover, mutation, selection, everything occurs in each population separately, except when we compute fitness. That's when we need an individual from each population. An encoder and an encoder individual and a representation individual come together, and the former decodes the latter, and that's how we get an individual, an entity that we can compute fitness for. And we showed that this schema, which is the heart of the OMNIREP algorithm, we showed that it can be used advantageously in various problems. I'm going to focus on evolutionary art right now. And what we did here is we are basically looking at the idea of there being a target image, okay? And we're not so much interested in replicating precisely the target image, but it's kind of a standard of beauty, okay? We want to work our way evolutionarily towards it. And the way we do it is we have two populations. One is representations and one is encoders or interpreters. And you take an individual from one population, an individual from the other population together, okay? The interpreter interprets the representation. That eventually ends up being an image. We compare that image to some target image we're interested in, and we can just compute fitness as mean absolute error between the pixel values. So what do we mean by encoding or interpreter and representation? We came up with three scenarios where the representation can be a list of pixel indexes, or it can be shapes, or it can be shapes, by shapes I mean polygons, or it can be circles. That would be the representation, and the interpreter would tell us how to decode these pixels or these shapes, okay? By decoding, for example, if we have a bunch of pixels in the representation, then the interpreter will tell us, well, what you do now is you look at these pixels, and then at these pixels, and then at these bunch of pixels, and you color them thus, okay? So we have two entities, one in each population, and ultimately they come together to produce an image, and all the dirty details are in the paper, of course. We were able to make, to evolve some pretty nifty pictures, and I think, as often happens in evolutionary art, it's not so much the final product, which can also be nice, but it's also the evolutionary progression that is interesting, and I think we evolved some pretty nice ones. So in conclusion, we found that OMNIREP is able to solve all kinds of problems successfully, not just evolutionary art, as I mentioned a couple of minutes ago. Usually we end up with better encodings, okay? For example, more compact encodings that have evolved. I want to mention another coevolutionary algorithm of ours called SAFE, where we have two populations. One, a population of solutions. The other is a population of fitness functions. So the fitness function evolves along with the solutions. And I think this is kind of a nice way to end this talk. Something that Ken Stanley wrote a couple of years ago. While a good algorithm is sometimes one that performs well, sometimes a good algorithm is instead one that leads to other algorithms and new frontiers. And hopefully this is the case with OMNIREP. We have all kinds of ideas for future work. We use a pretty small color palette. We can increase that. It's more sophisticated encoders or interpreters, more sophisticated shapes and overlapping shapes and hybrid shapes and uses of novelty. So there's all kinds of places we can go. But I think that right now I'm just going to go to the end. And that's it. Thank you very much.